Welcome to the next video in Abstract Linear Algebra. This is video 3, and here we're going to discuss exercise 3 at the end of chapter 1, section A. So the exercise asks us to find two distinct square roots of I. Now, let's summarize what that really means, which is that we need to find some two complex numbers, alpha and beta, such that they are distinct, so they can't both be the same ones, and they must have the property that when you square them, the result is I. Now, one way to solve this problem is purely algebraic, and I think given all that was discussed in the textbook, this is perhaps the intended solution, because I don't think they've really told you enough about the geometry of complex numbers to be able to solve it in a somewhat slicker way. But it is a little sort of unfortunate. Okay, well, let's talk briefly about the algebraic solution. So we're going to assume that alpha is a plus bi. And then what that must mean is that alpha squared, if you work out the complex arithmetic, you'll get that it's a squared minus b squared plus 2abi. And we are setting that equal to I. We're trying to search for the real values a and b such that this equation is satisfied, and it entails that a squared minus b squared must equal 0 because that is the real part of I, and it's the real part here. So since the real parts must match, then a squared minus b squared is equal to I. Also, the imaginary parts must match. So this 2abi, well, the 2ab, that's the real coefficient of I, and that must match the real coefficient of just the number I. So its real coefficient is 1, so 2ab is equal to 1. And you can continue solving, and presumably with good enough algebra skills, you'll get there. You'll find the answer. But I would like to just at least demo for you that if you do know the geometry of complex numbers, then you can find the answer more elegantly, and the geometry of complex numbers is just a really wonderful, useful theory. So let's just try to go through it briefly. I hope, given that I'm going to do this so quickly, I hope that it makes sense, but let's see how this goes. So first of all, let's talk about the geometry of complex numbers. If you take any complex number, and here I'm just writing down a random, just for demonstration purposes, a random complex number, which is 3 plus 2i, and we can identify that with a point in the plane by making a horizontal real axis, and so we're going to go out a distance of 3, because that's the real part of our example complex number, right? So you use the real axis to go out along as far as the real part indicates. Then you go vertically, and the vertical axis is our imaginary axis. So we go up by 2 because that is our imaginary part. And so we get to this coordinate 3, 2, or what we tend to write as 3 plus 2i. So that's just giving a brief story of the geometry of complex numbers. Of course, the imaginary number I is going to be right here, 0 real part, 1 imaginary part. So that is the location of I in the complex plane. Now, it turns out, and we could, if we had a whole bunch of time to talk all about the complex numbers, we could explain this thoroughly, but it turns out that multiplying by I, right, taking any number and multiplying by I, always corresponds to a 90-degree rotation. So to get some familiarity with why that would be, imagine taking the complex number I, let's just start there, and multiply that by I, because it's so easy, right? Well, what do you get when you take I and multiply by I? You get I squared, and that is -1. So it sends you from, right, so taking I, multiplying by I, sends you over to -1, which is here on the real axis, and it takes almost no thought to realize that, yeah, that's a 90-degree rotation. So at least in that specific case, we're seeing that, yes, multiplying by I gets you a 90-degree rotation. Let's do some more just to get a feel for this. What if I were here, right? Let's take the number -1 and multiply by I. What do you get? Well, you get -I, which is here. And that corresponds to another 90-degree rotation. Right, because it's -1 times I. So let's do it again. Let's take this, multiply by I, and where does that send you? Well, if we're doing -I times I, that's the same thing as -I squared. I squared is -1, and that is 1, so it sends you here to the point 1, which again is a 90-degree rotation from where we were. So this seems to confirm, and you can just keep going around and around and around, and this keeps getting you 90-degree rotations. And my claim is that even if you did it to a number like 3 plus 2i, you would again get a 90-degree rotation. Now, we're not going to go sort of over that too much. It's just a promise that if you multiply this by I, it'll send you over to some point over here that is like taking, right, if you take this line and spin it by 90 degrees, that is the result of multiplying by I. So that's a promise that multiplying by I gets you a 90-degree rotation. There's a whole theory, right? Adding two complex numbers is like vector addition. Multiplying complex numbers is a rotation and a scale. There's this whole theory of it. It's beautiful. It's a wonderful thing to learn. But for now, we're trying to be brief, so I'm going to leave it there. But what can we do with all of this theory to answer this particular exercise? Well, it would indicate that the solution to the problem, right? We're trying to find a number which when you square it, you get I. So maybe if I'm trying to get to I by squaring, and squaring basically is going to double your angle. If multiplying by I is a 90-degree rotation and I itself has a 90-degree angle, well, then you kind of think, well, maybe what we want is we want a 45-degree angle. This is not a rigorous, right? Like this is, again, right? If we were going to give a lot of detail, then we'd really slow down for all of these things. But I'm just going to suggest that maybe what we want then, like to have something where, when you square it, you get I, is maybe we want a 45-degree angle here so that when we square it, right, we multiply it with itself, you get 45 degrees plus another 45 degrees, which sends you over to 90 degrees. And if that story is correct, then the number that you want is this number here, right? You would want, like with that being an angle of 45 degrees, the real part would be the cosine of 45 degrees. The imaginary part would be the sine of 45 degrees. In this particular case, it turns out that both of those are root 2 over 2. And here is the solution, right? So there is actually one of the two requested square roots of I. If you take this thing and square it, you should get I. Okay, that is fantastic and I think very interesting, but and you would get the same thing if you solved the system of equations, but there still remains the question, what about that other root? Well, I'm not going to fully answer it. I hope I've been provocative enough to get you interested in thinking in terms of the geometry of complex numbers. So rather than fully answer the question, I'm going to leave you with this suggestion. If you had an angle sweeping 225 degrees and you look at the number that's right there, well, what happens when you double that angle? You get 450 degrees. And if we want to think about how that, like maybe fits on the unit circle or whatever, we can take away 360 degrees and get 90 degrees, which is the angle of I, and therefore that's very suggestive. So I'll let you think about, from this picture, what am I suggesting is the other square root of I?